Ocarina of Time is a game that needs no introduction. Let's make the Lens of Truth. A couple of disclaimers before we get started. There are probably many ways that you could do this, but I'm going to do the one that I think is the most intuitive and probably what the Ocarina of Time team did anyway. And the way it's going to work is we're going to have a plane that's right in front of the camera, and that plane is going to change values in the stencil buffer, which is going to reveal or hide different objects. And a key press will just activate and deactivate the plane, and that's going to be like turning on and off the Lens of Truth. And another disclaimer, we're actually going to be implementing the one from Majora's Mask, not Ocarina of Time. And the reason for that is Majora's Mask has this kind of interesting animation that plays when you start and stop the Lens of Truth, and I just think it looks a lot cooler, so we're going to be making that one instead. As always, everything from this tutorial will be placed into a GitHub repository, which will be linked in the description. So check that out if you want to download the files for this tutorial. Here's a scene in Unity for us to use, and I've gone ahead and added some objects already. So if we look at this player object, this is really just an empty game object, but I've attached a character controller and this player controller script. And the combination of these two things is going to give us some pretty basic FPS controls. The script will be available in the GitHub repository for you to download, and I'll also talk a bit more about that later. You can see we also have this camera transform slot, and I've gone ahead and just drag and dropped the main camera into this position right here. And if we look at the children of the game object, we have this player capsule, which is really just Unity's standard capsule. And you'll notice it has no collider on it, and the reason for that is because the character controller already has a collider of its own. You can also see we have the main camera as a child of the player game object, and the reason it's a child is because when we move the character controller or rotate it, we want the camera to move and rotate along with it. And everything here should be the default settings, but I have gone ahead and moved the camera up slightly so that it's positioned at the head of the player game object. There's also some objects in front of the player capsule, and let me go ahead and reveal this one right here. So we have this red cube, this purple cylinder, and this yellow sphere. And the purple cylinder is just a normal cylinder, there's nothing attached to it. But the red cube has this fake object script attached to it. And this sphere also has another custom shader, and this is using the hidden object shader. So the red cube is supposed to correspond to things that will turn invisible when we have the Lens of Truth activated, and the sphere corresponds to objects that will turn visible when it's activated. So if we look at the shaders for those, the red cube has this fake object shader on it, and this is just a standard surface shader, but I've added this block right here, and I've also changed the Q to transparent +1. And this is going to make it so that it renders after basically everything else in our scene. And this block right here tells it to only render if there's a 0 in the stencil buffer. If we look at the hidden object shader, you can see that it's almost the exact same. We still have that Q transparent +1, and we have the stencil block here. The only difference is it's only going to render if there's a 1 in the stencil buffer. And by default, the value in the stencil buffer is 0, so we don't see the sphere. Before we move forward, we should talk a bit about the stencil buffer. And I've talked about this before in other videos, so I'll be brief here, but if you want a more detailed explanation, I recommend you check out my antechamber video. The stencil buffer is just a 2D array of numbers, and it's equal to the size of the screen. So for example, if your game is running at a resolution of 1920 by 1080, then your buffer is going to have 1920 columns and 1080 rows. And by default, the number in the stencil buffer is going to be 0. And the buffer actually matches up with the pixels on the screen. So for example, the number in the bottom left corner of the buffer is going to correspond to the pixel in the bottom left corner of the screen. And the way that we're going to interact with the buffer is through shaders. So for example, if I wrote a shader and told it to put the value 1 into the stencil buffer, and then I put it on an object, when that object renders, whatever pixels it's touching are going to have their corresponding buffer values changed to 1. And instead of writing to the stencil buffer, we can also check the value in the stencil buffer. And that's nice for us because what we can actually do is check the value in the stencil buffer, and then based on that value, we can decide whether or not we want to render the object. Let's look at a more concrete example of how we can use the stencil buffer. So here's the scene where a monkey and a box are behind a picture frame. And when I move the camera around, you can see that the monkey disappears when we're not looking at it through the picture frame. So what's going on here? So first I have some code added to the shader of the frame that turns it invisible so that we can see through it. And after that, I added some code to the shader of the picture frame that tells it to put a 1 into whatever pixel the picture frame is touching. So I've added some 1s here for reference, but of course these wouldn't be to scale. There's probably thousands of pixels inside the picture frame. And after creating the monkey and the box, I added code to those shaders, which tells them to only render the object if they can see a 1 in the stencil buffer at that location. And the only locations where there's a 1 in the stencil buffer are going to be behind the picture frame. So you can see that when we move behind the picture frame, we don't see the monkey anymore because now there's a 0 in the stencil buffer for that pixel. So this combination of transparency and stencil buffer changing and reading is going to be how we make the lens of truth. When we turn the lens of truth on, we're going to have it put the value 1 into the stencil buffer, and so any object which is looking for a 1 is going to be rendered suddenly, and any object which is looking for a 0 is going to stop being rendered, because now the 0 has been replaced by a 1. Alright, so to make the plane, we're actually just going to use Unity's basic game objects, and I'm going to use the plane and the cylinder. So let me go ahead and make the plane right now. So I'll call this lens plane, and then let's rotate it maybe -90, and then I'll put it at 2 and 1 and 2, and let's decrease the size to maybe 0.1. That looks pretty good. And then what we need now is to make a shader that's going to apply a red tint to the plane. And the reason for that is that this plane is going to be the red background that shows up when the lens is active. So if I go ahead and right click and create an unlit shader, I'm going to call this red tint. And then I'm going to create a material and apply it to the plane. Now let's go ahead and double click to open up this shader. Alright, this is what a standard unlit shader looks like in Unity with no changes yet. So first, let's turn this thing transparent. So I've talked about this in detail in my antechamber video, so I'm going to be kind of brief here. So first we can change the render type to transparent, and then we can assign this to the transparent queue. And this just tells it to render after all of the opaque objects. And we're actually going to put it right after the transparent queue. So we're going to write transparent +1. And then what we're going to do is write blend source alpha 1 minus source alpha. And this is a line that you need to add in order to tell the object how to blend with the objects behind it. So you can kind of think of these as two percentages. So the percentage of this object that's going to show up is the alpha, and the percentage of other objects behind it that are going to show up are 1 minus source alpha. And that's kind of all we need for transparency, but if we go back and look at Unity, you'll see that nothing has really changed. And the reason for that is we haven't changed the alpha value. So if you want to make something transparent, you have to decrease its alpha. And we could do that with code right here and just change call.a to 0 or something. But I'm actually going to create a property that will allow us to change it from the editor. And I'm going to call that property tint. And in the editor, it'll show up as tint color. It's going to be a color, and the default value will be all 1s, which is just white with an alpha value of 1. And then now that we've declared it up here, we need to declare it down here in the code. And it's going to be a float 4, so we can just write it right here. And then what we need to do is multiply it on to the final color, which is returned. So tint. So now if we go back to Unity and see what we have, again, there's nothing here. And the reason for that is we haven't changed the tint color yet. So if I go here, click on tint color, change it to red, you can see that the plane changes red now. And Unity actually gives us an alpha slider right here, which is pretty convenient. So I'm just going to dial it down to maybe somewhere around 100. I think that looks pretty good. And then maybe the tint will be a little lighter. And yeah, I think that looks pretty good. All right, now let's make the cylinder that's going to go in the middle, which is where the invisible objects will actually show up. So I'm going to create a cylinder here, and then it's way too big and it's also vertical. So let's change the rotation, not Y, I think around X maybe. There we go. And then let's just change that to 90. All right, and then let's try to center this as best we can. I think that looks good. And then we're going to decrease the scale. Let's see. So we can have X be maybe, I don't know, 0.7, and then Z also 0.7. And then Y, we're going to need to make really, really small. So, yeah, honestly, even smaller than that. Maybe 3 zeros and a 3. I think that looks pretty good. Okay, so then what we can do is work on the shader for the cylinder right here. And this is the shader that's actually going to interact with the stencil buffer. So I'm going to go ahead and create another unlit shader. And maybe I'll call this lens effect. And I'm going to go ahead and create a material from that shader and apply it to the lens. There we go. And let's go ahead and open up that lens effect shader. All right, so for this shader, we're going to do almost the same thing we did for the other one. So first, let's just turn it transparent. So I'm going to turn the render type to transparent. And then the Q is going to be just transparent this time, no +1. And I'll explain that in a bit. And then again, we'll have that blend, source alpha, 1 minus source alpha. And then what we can do is actually just directly change the alpha of this object. So to do that, we can say call.a is equal to 0 with a semicolon. And this is going to say for every pixel, we want the alpha value to be 0, which means every pixel is going to be completely invisible. And then we want to do one more thing, actually. We want to have this shader interact with the stencil buffer. So to do that, I'm going to write stencil, the set of curly braces, and then I'm going to write ref1. And this line just creates a variable named ref and puts the value of 1 into that variable. Then what I'm going to do is comp always. And this line is kind of saying just ignore the stencil buffer. We're just going to render this object no matter what's in the stencil buffer. So it's almost like ignoring the stencil test, if you know what that is. And then what we're going to write is pass replace. So this says once the object passes the stencil buffer, which it's always going to do, then replace whatever's in the stencil buffer at this pixel with the value of 1. So basically this whole code block just replaces whatever's in the stencil buffer at whatever pixels this object is touching with the value 1. And then there's actually one more thing we need to do here, and that is to write zwrite off. And again, this is something I explained in the antechamber video, but this is basically turning off the ability of this shader to write to the depth buffer. And the reason you want to do that is because of the way Unity handles transparency. Basically, if there's an object that renders after a transparent object, and it's behind the transparent object, it's not going to show up unless we tell the object not to write to the depth buffer. So that's why we do this. All right, now back in the editor, you can see that it looks like our cylinder has just completely disappeared, and that's because of the transparency code that we did. But if I actually slide this plane over and put it in front of the sphere, you can see that the sphere starts showing up now, and that's because of the stencil buffer changes that we made. So let's make it so that we can actually see the kind of like transparent hole in the middle of this plane. So to do that, I'm going to go back to the red tint shader, and then what we need to do is actually have this shader interact with the stencil buffer as well. So let's go ahead and create a stencil block. And what I'm going to do is put the value of 0 into ref. And then I'm going to write comp equal. So this line just says look into the stencil buffer at these pixels and make sure that the value in the stencil buffer is equal to 0. If it is equal to 0, then we're going to continue drawing this object. If it's not equal to 0, then we're not going to draw the object. So I'm going to Control S to save and then back in Unity. And you can see now that we have this hole in the middle of the red tint. And if I slide it over, now you can see the sphere inside the hole. So that is essentially all we need to do for the actual lens of truth effect. And one last note on the stencil buffer. I'm going to go back to the red tint shader, and I'm going to change this line from +1 to -1. So now this red tint shader is rendering right before the lens effect shader. So I want you to try to think to yourself what this might do to the plane and the cylinder. And if we go back to Unity, we can see that the cylinder completely disappears. So why is that? Well, the reason is the plane is rendering before the cylinder has a chance to put the value of 1 into the stencil buffer. So in other words, when the plane checks the stencil buffer, the value is going to be 0 everywhere. So that's why we have this set to Q transparent +1. We want to give the lens effect shader a chance to put the value 1 into the stencil buffer, then we can render the plane and then have it check the stencil buffer for 0 or 1. And now what we need to do is put this thing in front of the camera so that wherever we move the camera, the effect will follow. And first what I'm going to do is rename this, and I'm going to call it lens cylinder. And then I'm also going to create an empty game object. And this is just going to hold both the plane and the cylinder to keep them unified as one game object. And I'll just call this lens of truth. And then I'm going to put it at the same position as the cylinder and the plane. And so I think, what was it? It was like 2, and then 1, and then 2. That looks pretty good. And then what we can do is just go ahead and make these both children of the lens of truth. So now wherever we move this thing, the cylinder and the plane will follow. Okay, and now what we need to do is put it right in front of the camera that's on our player. So I'm going to drag it forward and then drag it up. And I think the Y needs to be 1.5 and the X needs to be 0. And now we kind of need to move it forward and stop it right when it starts clipping with the camera. So if we move it about there and then check the game camera, you can see it hasn't clipped yet. And then a little bit more, and still good. And if we move it here, I think it should start to clip. And actually that still looks okay. So maybe we could try 0.3. How does that look? Yeah, things start getting weird. So maybe, I think 0.33 is probably good. Let's see. Yeah, that looks pretty good. Okay, so now that this is positioned correctly, we can actually just go ahead and make it a child of the camera. And now if we hit play, I think we should see that wherever we move the camera, the frame, the plane and the cylinder will follow. And that's exactly what we see. So back in the editor, now what we need to do is actually change the scale of these two. And we want them to kind of like just overlap with the edge of the camera. So I'm actually going to decrease the circle in the middle a little bit and focus on the plane right now. So if I click plane, let's change the X and see what happens. So yeah, if I make it smaller, you can see that the edges don't line up. So if I try maybe 0.5, maybe 0.8. Yeah, that looks pretty good. I'll try 0.8. And then let's see, Z. Yeah, it looks like 0.4 is pretty good there. And then let's look at the cylinder now. So if we increase X a little bit, we want it to be just at the edges. So I think 0.7 should be pretty good. And then if we increase Z, yeah, you know what? Let's increase this to maybe 0.9, and then we'll have this be 0.9 as well. I think that'll be pretty good. And then if we press play and move the camera around, we should see that sphere and the cube has disappeared. And that's because the camera is being followed by that cylinder object. All right, that looks pretty good. All right, now what we're going to do is actually work on these scripts, which will allow us to activate and deactivate the lens of truth. So first things first, I'm just going to grab these materials and these shaders and move them out of the way because we're done working on those. So now let's go ahead and right click and create a C# script. And for the sake of simplicity, I'm just going to call this LOT. And then we can double click to open that up. And let's see. So we can go ahead and get rid of this, and we can actually get rid of the update function as well. And what we need here is to get a reference to those two children in the lens of truth game object. So to do that, what I'm going to do is write game object, and I'll call the lens, or I'll call the cylinder lens, and I'll call the plane that's around the cylinder the border. And then we can just end that there. And then in the start function, what we can do to grab those objects is, if we go back to Unity, you can see the cylinder is first, and then the plane is the second child. So what we can do is write lens is equal to transform.getChild. And then I think what we can do here is just write 0 to get the first one. And then I'm going to write game object. So that will give us the child as a game object. And then we can do the same thing with border. So I'm going to write border is equal to transform.getChild, and then 1 for the second game object. And then just write game object here. So now that we have both of them, what I want to do is start, when the script is loaded, I want to start the game as having the lens of truth off. So what I'm going to do is write lens.getComponent, and the component is going to be the mesh renderer. So this is the thing that renders the object to the screen. And then what I'm going to do is write dot enabled is equal to false. So this is really just saying at the start, when the script is loaded, turn off the renderer of the lens. And then we can actually do the same thing for the border. So I'm going to write border.getComponent mesh render.enabled is equal to false. And let's see if I did that right. And back in Unity, before we see those changes, what we actually need to do is put this LOT script onto the lens of truth game object. And you can see now it's one of the components. And if we press play, hopefully we should see that the cube is still there, and then the sphere disappears. And that's exactly what we see. And that means that the cylinder is no longer being rendered, which means it's not putting the value of 1 into the stencil buffer. And now what we need is a way to turn the lens back on. So I'm going to go back into this LOT script, and then I'm going to add a function down here. And this is going to be a public function, which means that it can be accessed from other scripts. And then it's going to have a void return type because it's not returning anything. And then we're going to call it lens activate. And then for now, what we're just going to have in here is the ability to turn those mesh renderers back on. So I'm going to write true here, and I'm going to write true right here. So before we can use that public function, we need a way to record when the player presses a key. And for that, I'm going to go inside the player controller script. And you don't really need to understand most of this, but basically every time update is called, we have this movement function, and this just gets the WASD keys to allow for walking forward and backwards, left and right. And then this camera function, which gets the input from the mouse to rotate the camera. And I'm going to go ahead and add another function, and we're going to call that interact. Oops. And we can go ahead and create that down here. And just like the other ones, it's going to be private and void. And all this is going to have is the ability to record a key press. So what we're going to do is say if input.get key down, and then you can do whatever you want. I'm just going to do E here. So if the player presses the key E, right now let's just do debug.log to make sure that this function is working as intended. So I'm going to go ahead and debug.log the word pressed. And now back in Unity, if we press play, and then I press the E key, you can see that in the bottom left, we have the word press passed to the console. So we know the interactivity is working. So now what we need to do is have a way for the player controller script to talk to the LOT script in order to grab that function we created. So to do that, I'm actually going to go to the Lens of Truth game object, and I'm going to put this into a tag. So I have this Lens of Truth tag I already created, and if you want, just go to add tag, type that in by using this plus right here. And then we're going to put this Lens of Truth game object into that tag. And the reason we do this is because a tag is a really easy way to grab a game object or a group of game objects from a script. So now that we have that, what we can actually do is go back into our player controller script. So back in the player controller, what I'm going to do is write LOT lens script. And this is what's known as creating an instance of the LOT class. And the LOT class basically just refers to this script right here. And to get the script, we first need to get that game object. And that's where the tag comes in handy. So what I'm going to do is write lens script is equal to game object dot find. And then with the find function, all you have to do is pass in the name of the tag. So the name of our tag is lens of truth. And there's only one game object with that tag, and it's the lens of truth. And this right here is equal to that game object, that empty game object holding both the cylinder and the plane. So then what we can do is write .get component, and I'm going to write LOT, which is the name of the script. And then add a set of empty parentheses for some reason. And then this right here is the script. So now that we have access to the script, we have access to that public function we made, this lens activate right here. So now what I can do is go down here, and instead of writing to debug.log, what I can actually do is write lens script.lens activate, and then a set of close parentheses because it's a method. And if we control S and go back to Unity, and now if I press play, so when I press the E key, we should see the cube disappear and the sphere reappear because the stencil buffer is being written to again. And that's exactly what we see. So pressing E reactivated the lens of truth and the cylinder. So now we can see that we're interacting with the stencil buffer again. So that's all well and good, but we need a way to actually turn the lens on and off. Right now, when we interact with it, all that happens is it turns on. So let's go back into our LOT script, and we can see that this lens activate function only has the ability to set the renderer to true. It doesn't have the ability to set it to false. So what I'm going to do is create a conditional statement here. I'm going to say if the lens is active, so this will be a Boolean that we create later. If the lens is active and lens activate is called, let's turn the lens off. So I'm just going to copy paste these in here. And then we can say else, if the lens is not active, let's turn it on. So I'll just grab these and move them right here. And that looks good. So for this to work, we need to declare a Boolean. So let's do that up here. So I'm going to say private bool, meaning just true or false, lens active, and let's start it as false, meaning the lens is going to start not activated. So if the lens is active and we call lens activate, we're going to turn it off. So then we need to set that Boolean to false. So what I'm going to do is say lens active is equal to not lens active. So if lens active is true, it's going to change to false. And then likewise down here, if lens active was false, and then we turn on the lens with these functions, we need to set lens active to true. So lens active is equal to not lens active. So if it was false, it's going to turn to true. So let's Control S and go back to Unity. And if we run this, let's see what happens. So I'm going to press play. And then if I press E, you can see the sphere appears and the cube disappears. And then if I press E again, they reverse, they go back to normal. So we can tell that our script is working as intended. You probably noticed something's wrong, and that's that we don't see that red plane, that clear tint that turns on when the lens of truth is activated in the game. So let's see how we can get that running. And what we need to do is basically change the scale of the cylinder. So the scale needs to be smaller when the lens is active, and then it needs to expand when the lens is turned off. So the way I thought of doing this is by creating some vector 3s corresponding to the scale. So I'm going to declare 2 up here, and they're going to be expanded scale, meaning the cylinder is at its largest, and contracted scale, meaning the cylinder is at the small scale. So to get those, what we can do is also declare a float. Let's call that start scale. And this is just going to be the scale when we first run this script. So if you think about how we rotated the cylinder, and when we want to expand and contract the lens, what we really need to do is change the X and Z components of the cylinder. That's going to change it in that horizontal and vertical axis, which we're looking at through the camera. So what I'm going to do is say start scale is equal to lens.transform.localScale.x. So the X and the Z scale of the cylinder is the exact same. So this is equivalent to getting the Z scale. And the reason I use local scale is because that's typically what you use when you're getting the scale of a game object, which is a child of another game object. So right now, I believe in the editor, this is at 0.9. So that's what we're getting right here and putting into scale. And then what we can do is say expanded scale is equal to a new vector 3. And what we're going to do is say start scale for the X, and then we're going to say 0 for the Y, and then we're going to say start scale for the Z. So this represents the lens when it's at its most expanded state. And then what we can do is say contracted scale is equal to expanded scale, and then I'm going to divide it by 2.5f. So this is just going to return another vector 3, but the start scale is going to be divided by 2.5, so it's going to be much smaller. And then what we can do is when the lens of truth gets activated down here in this function, what we can do is actually set the local scale of the lens to this contracted scale. So let's set lens.transform.localScale equal to this contracted scale. Contracted scale like that. And then when the lens gets deactivated, let's make the lens giant again. So what we can do is say the local scale is now equal to the expanded scale. And when we go back to Unity, let's see what that does for us. So I'm going to hit play. And then now when we press E, you can see that we have this red tint. And that's because we changed the X and Z scale of the cylinder to shrink down to this size. And then if I press E again, the lens gets deactivated, so you can't really see it, but the cylinder is actually increasing to that larger scale. And you might think that has no purpose, but what we're going to do now is actually animate the expanding and contracting of the cylinder. So then that's where the expanded scale is going to come into play. So to get this animation running, we're actually going to use something called a coroutine. And I know I say this a lot, but I explain coroutines in detail in my Gate of Time video. So I'd recommend you check out that video if you want a detailed explanation. But basically, a coroutine is a special kind of function that will run in parallel to the rest of your code. And then it has the ability to pause for certain periods of time and will just destroy itself whenever the runtime is finished. The runtime of the function is finished. And it's pretty useful if you have animations that need to run for a set period of time and then stop. So let's go ahead and make a coroutine down here. So it looks like this, IEnumerator. And then let's call the coroutine lens contract, like that. And then it's going to give you an error straight away, and that's because a coroutine needs to have a special return type that looks like this. Yield return null. And that looks super weird, but basically this is just saying pause for a frame, and then move on. So basically, all this coroutine is going to do is pause for one frame and then destroy itself because there's no other code. So what we can do is actually move some of the code up here into this lens contract. So remember, lens contract is going to be called when the lens is activated. So what we can do is actually copy this code from in here and then just pop it right down into this coroutine like that. And then that looks good. And then what we need to do is actually call the coroutine from this function. So the way to call a coroutine is to write start coroutine and then just add the name. So lens contract like that. And then so when this else block is called, it's going to start that coroutine. And then the coroutine is going to set the scale to the contracted scale. And then we're going to enable the mesh renderer. And then basically the coroutine is going to pause for a frame and then end itself. So let's go ahead and save and go back to Unity and see what we have. And if I hit play, what we can do is press E to try and activate it. And we get the exact same thing as before. So now we have that same code, but it's in a coroutine. And that's going to allow us to animate it. So let's do that now. So back in the script, what we're going to use is something known as linear interpolation, or Lerp for short. And if you've never used it before, basically it's a way to smoothly transition from one state to the next. So in our case, state 1 might be the expanded scale, and then state 2 is the contracted scale. So if we lerp between these scales, basically Unity is going to calculate every step of the way for us to smoothly go from one to the other. So I think the best way to explain it is to just show you. So what we can do is get rid of this. And I'm going to copy this line. And I'm going to put it right here. And I'm going to say the local scale is equal to vector3.lerp, which means just lerp between vector 3s. And I think maybe this needs to be capital. Is that right? Oh, no. Lerp. There we go. And then, so what we do is provide the starting vector, the ending vector, and then a percentage. So the starting vector is going to be expanded. And the ending vector is going to be contracted scale. Nope, didn't spell that right. Contracted scale. And then the last thing is going to be the percentage. So basically the way this works is 0% corresponds to expanded scale. So if I passed in 0 right here, the result would just be expanded scale with no changes. Whereas if I passed in 1, the result of the lerp would be contracted scale with no changes. And then, for example, 0.5 would be the exact midpoint between these two scales. So if we pass in a variable, what we can do is change this variable over time. And then that will smoothly transition from this scale to this scale. So in order to change the percentage, we actually need to be in a while loop. So I'm going to write while, and then I'm going to say percentage is less than 1. So while percentage is less than 100%, what we can do is increase percentage by a certain speed, which we'll define later. And then we can put this transform inside the while block. So what's going to happen is every time this runs, we're going to increase the percentage, and then we're going to lerp based on where that percentage is. And then once percentage hits 100%, we're going to stop. But there's one problem here, and that's that we're not really pausing. This would all run basically in one frame, which we don't want. So what we can do is take this yield return null, which pauses for a frame, and then we'll put it in here. So every time the local scale changes, we're going to pause for a frame and then return to the top of the while loop. So there's actually a problem with this code that I'm sure some of you have noticed. And the problem is the percentage is going to increase at a different rate depending on the frame rate. And the reason is if we're running at 15 frames per second, then this while block will run 15 times in 1 second. And say if our speed was, I don't know, 0.01, then that means percentage is going to end up at 0.15. Whereas if we're running at 30 frames per second, then after 1 second, percentage would be at 0.30. So in other words, in the same amount of time at different frame rates, we'll be at a different position in our Lerp. We might be closer or farther from the contracted scale. And obviously we don't want that. We want the animation to be the same regardless of the frame rate. So to fix that, what we can actually do is multiply speed by time.delta time. And this delta time is really just the amount of time that has elapsed from the last frame to the current one, as you can see right there. So in other words, if we're running at 15 frames per second, time.delta time is going to be larger. If we're running at 30 frames per second, time.delta time is going to be smaller. And the reason that fixes our problem is even if we're running at 15 frames per second and the while block is run less times, percentage is going to increase by a larger amount each time. So we're going to end up at the same spot as if we were running at 30 frames per second. And the last thing we need to do to get this to work is just declare this percentage and speed variable. So what I'm going to do is go here and write float percentage. Actually, let's make this a private float. Private float percentage is equal to 0, and we'll make it a float. And then we can declare private speed, private float speed, sorry. And I think 2.0 would be a good value. So speed is going to be 2, percentage is going to start at 0. And let's go back to Unity and see what happens. All right, so if I hit start, and then I'm going to press E, and you can see we get this nice animation from the expanded to the contracted state. But you'll notice if I press E again, there's no animation, obviously, to expand the lens. So let's try and do that right now. So to get the other animation, we're just going to make another coroutine. So down here, I'm going to write I enumerator lens expand. And then we're just going to go ahead and grab all this stuff up here and then paste it down here. And let's see. Then up here, we're going to replace that by starting the coroutine. And it's going to be lens expand. And then if we go down here, we don't really need this anymore. And what I'm going to do is actually put the while block before the renders are disabled, because if we disable them first, obviously we're not going to be seeing any of the animation that we make. So I'll have the while up here. And then another change is that the percentage should be at 1 when we finish the last one. So percentage is going to go from 1 to 0. So I'm going to write while percentage is greater than 0. And then we'll have our block here. And then we're actually going to use the same Lerp. We're going to have the expanded scale be the start at 0, and then the contracted scale be the end at 1. And the reason we can do that is because we're actually going backwards. We're going from 1 to 0. And then obviously we need to have percentage change, but instead of increasing, we're going to have it decrease every frame. And there's an error here, and that's because there's no yield return null. So let's go ahead and grab that. And we will put it right here, just like last time. So let's go back to Unity and see what that gets us. So I'm going to go ahead and hit play, and let's see what happens. So I hit E, we get that nice animation, hit it again, and we get another nice animation. That looks pretty good. And you can see that the animation finishes and then the render is disabled. So you can still see everything until the red tint goes fully out of view, and then everything reverts back to normal. And I think that's the way it looks in a Majora's Mask. So I'm going to leave it like that. And we're not done yet because there's one more problem, and that's if we reverse the animation while, for example, it's expanding, you can see it pauses. It doesn't go back. And you might want that for your game, but I want to make it as consistent with Majora's Mask as possible. So let's go back into the code and make sure that it doesn't stop like that. So I think the issue is that the coroutines aren't stopping when we start the other one, so they're sort of fighting with each other to change the Lerp. So to fix that, we're just going to stop whichever one is running and then start the other one. And there are multiple ways to stop coroutines. Some of them work better than others, and I'm not sure why. But the one that works for me is stop all coroutines, like that. So there's only one coroutine running at a time, so this is just going to stop that one. So it shouldn't cause any issues for us if we just stop all of them. So I'm going to put that in both of these if statement blocks. And then if we go back to Unity, let's see what happens. I'm going to go ahead and hit play. And let's try to stop the animation before it finishes. And you can see it bounces back. So I think that looks pretty faithful to the original. And I hope you like it too. And I hope to see you in the next video.